So we have been up till now basically treating treating all of our objects as if they could be treated as particles. So their shape didn't matter, whether they were rotating or not didn't matter. And now we're going to start to change that. And so the first thing we're going to do is we're going to come back and we're going to add on the idea of rotational motion. So how does something rotate? And what we want to do with this sort of video is set up the idea that the language, the terminology, the way we think about translational motion should line up with exactly the way we want to think about rotational motion. So when we talked about translational motion, we started by talking about the concept of position. For a one-dimensional problem, we might use x to tell you where the position was for your particle. Well, in rotational motion, we're going to use angular position. And again, what we're going to see is everything over here is going to be a Latin letter, right? So letters of the alphabet as we sort of recognize them. Over here, we're going to use all Greek letters. So Greek letters tell us that we've got stuff that's dealing with rotating. Or Latin letters tell us that we've got stuff that's dealing with things as they move around in space. So angular position basically just says, where are you at in terms of some rotational angle, in the same way that position says, where are you at in terms of some x coordinate. Well, if you want to talk about how the position changes, we define something called the displacement, which is nothing more than x final minus x initial. Well, in rotational motion, if you want to think about how your angle changes, you define what's called the angular displacement. And again, it's nothing more than saying the final angle minus the initial angle. When you care about how the position is changing with respect to time, we said that's called the velocity. And we talked about sort of two types of velocity. One is the average velocity, which cares about just what's going on at 2 points in time. So what was your initial position, your final position, subtract final minus initial, and then divide by the time between those 2 points. Or you could talk about the instantaneous velocity and say, what is your velocity at any particular instant in time? If you knew your position as a function of time, then you could use the derivative. So take the derivative of your position function with respect to time to give you the instantaneous velocity. Well, if we're interested in how our angular position changes with respect to time, we're going to talk about something called the angular velocity. This letter here happens to be a lowercase omega. So again, Greek letter, so this tells us we're dealing with rotational stuff. And we can talk about two different types of angular velocity. We can talk about the average angular velocity, which says I'm interested in what's going on between 2 points in time, so I need to know your angular displacement and the time between the 2 points you're calling your final and initial for the angular displacement. That'll give you the average angular velocity. Or I can talk about the instantaneous angular velocity, so what's going on at any particular instant. And again, I get that from thinking about the angle as a function of time and then taking its derivative. So my angular position is a function of time. Its derivative with respect to time, that's going to give me the instantaneous angular velocity. When we cared about how our velocity changed with respect to time, that was the acceleration. And again, we had two forms, the average that cared about what was going on at 2 points in time, and the instantaneous that said, I can tell you what's going on with the acceleration at any particular instant simply by thinking about the derivative of the velocity function with respect to time. Well, if you care about how your angular velocity is changing, then you're talking about an angular acceleration. And this gets a lowercase alpha. So this, again, Greek letter, so it tells us rotational stuff. Again, there's an average angular velocity where I need to know the final and initial angular, an average angular acceleration where I need to know a final and initial angular velocity of my object, divide by delta time. Or the instantaneous angular acceleration where, again, I just need the derivative of the angular velocity with respect to time. So our definitions are exactly the same. The one big detail that we emphasized previously was we know that these things are all vectors. And sure enough, these things are also going to be all vectors. And so we'll talk about how we want to treat these as vectors in a second. Now, what did we use all these definitions for? Well, first thing we did is we said, well, we can work translational motion problems. So we set up 3 kinematics equations. 2 of them depended on time. One of them told you more about what was going on with the position. One told you more about what was going on with the velocity. And then we had a third equation that didn't have time. So this was if you thought you didn't need time to answer the question, you could start with this equation, and 99 times out of 100, sure enough, this would get you where you needed to be. There's a set of rotational kinematics equations, and again, what you'll notice is every time there's an x over here, there's a theta over there. Every time there's a v over here, there's an omega over there. Every time there's an a over here, there's an alpha over there. T, that's the same. And so these equations are exactly the same, and how you use them would be exactly the same. So there's 2 functions of time here. The first one you'd use if you know or want to know more about the angular position. The second one you'd use if you want to know more about the angular velocity. There's a third equation that we would use if we want to avoid dealing with time. So we don't know time, don't want to worry about having to go solve for it. Then again, this third equation is the way that we would go about solving the problem. The important caveat to remember was we said we could only use these equations when the acceleration was constant. Well, that caveat also holds over here. These equations are only valid if the angular acceleration is constant. The last detail we said is that, well, these things are vectors, but the way that we're going to sort of deal with them with rotational motion is simply going to be motion about a particular axis. And so that axis lies along a single dimension. And so we're really, with our rotational motion stuff, going to be working one-dimensional problems. And as always, in a one-dimensional problem, the fact that these things are really all vectors tells us that we need to keep track of the signs. So when things rotate different ways, clockwise versus counterclockwise, let's say, those 2 things have to have opposite signs. And we'll play the same sorts of games in terms of thinking about the relative signs of the angular velocity and the angular acceleration that we used when thinking about the velocity and acceleration in our translational motion problem. So if an object is speeding up as it rotates, then we know that the angular velocity and angular acceleration have to point in the same direction. Therefore, their signs have to be the same. If, on the other hand, something's slowing down as it rotates, then just the opposite is true. The angular velocity and the angular acceleration have to point in opposite directions. Therefore, they have to have different signs. So all the rules we talked about when we first started setting up kinematics problems and leading into working Newton's second law with vector problems here for translational motion, all those rules still hold for rotational motion. The one nice thing is we could do 2-dimensional problems over here. We're only going to, with our rotational motion, we're going to always sort of limit this to simply 1-dimensional problems. So the vector nature of this stuff is really going to be determined by what's going on with the signs. And so we'll keep that in mind as we move forward.